Good afternoon, and thank you for joining. My name is Arvind. I work with the Covalent team. It's the founding company behind the open source project called Cilium. And we're going to talk about, as I mentioned, the powerful new technique in Linux kernel called BPF, and how BPF can be brought to a Kubernetes cluster near you, right, so to speak, and deliver networking and security for Kubernetes, okay? So the agenda is roughly, we'll give you a little bit of an overview about BPF, then how Cilium uses BPF for Kubernetes. We'll try our hands and struggle with the projection and things like that with the demo and font size and terminals and KubeCon and kubectl and things like that. So hopefully that will go well. And then we'll take a look at some of the cool stuff that we are doing, which was also covered in a couple of previous talks. So I'll just mention that briefly towards the end. Okay, so I think in recent times, there have not that many aha moments in Linux kernel. And I think safe to say that for more than a decade or so, BPF is probably the most exciting kernel technology to come out. It's a pretty powerful technique, and it is already impacting a wide range of areas in Linux systems: operations, troubleshooting, networking, performance analysis, DDoS mitigation, firewalls, and things like that. It's not seems like it has gone into an auto mode or something. Let me go back. So it has been in use in prod for all of these companies at a large scale for a long time now, for more than 2-3 years as far as we know. And the gist of this technique is actually it's very simple. I mean, it's not like a overly complicated Linux kernel module or something that you need to wrangle with, install, and it's a built-in technology. And if you have used, any of you have used TCP dump in the past, this was the technique behind it, hence the wonderful name Berkeley packet filter. At this point, it's a big misnomer because it's not just for packet filtering. You can attach these small programs to many different types of system calls and kernel events. You can attach it to memory requests, to file descriptors opening. You can attach it to observe things for performance. You can attach it to do extra processing of packets, denying them, forwarding them, and things like that. So it's essentially small programs, bytecode programs. You write them in C and Python like a upper level language. It gets compiled into a bytecode. Before it is loaded and executed in the kernel space, it's verified so that there are no loops, there is no incorrect memory access and things like that. So there is a just-in-time compiler and a verifier. The JIT makes it efficient, so there is no interpretation going on. It's not like each and every bytecode is getting interpreted. It gets compiled into underlying CPU architecture. It's not a Linux kernel module. This is one of the questions that we got very frequently. It's just a technique, just like other Linux techniques that are available in the Linux distribution. And at this point, I think all major distributions have announced support for this. I think the last was RHEL 8, and they are working on backporting it as well. Ubuntu 18, AWS, Linux, pretty much all the recent instances, GKE, COS, I mean, you name it, it's SUSE, all major distributions have support for this at this point. And for those of you who just came in, the BPF part is essentially just a small bytecode program that you can attach to various system calls, okay? Beyond that, I don't know. So it is pretty powerful in what you can do if you attach programs. Like if you think about it, Linux kernel does a lot of things from packet processing, handling files, handling various devices and things like that. There's not that much observability into what it is doing, right? There's not that much room to change the behavior or to do extra processing unless you recompile the kernel. These are the couple of use cases that I pulled out because this is kind of telling of where we want to go with Kubernetes and BPF and things like that. One of the popular use case is around load balancing. So when the packets come in, you know the source and destination headers. And let's say you just want to forward it for TLS termination or further processing, then you can do it very efficiently. It doesn't have to go up the Linux stack, right? The packet comes in, you can just forward it somewhere at the very early stage. That's what the XDP part does. So you can see that Kubernetes also has a lot of load balancing going on, right? Like cluster IP, node port, they all have the underpinnings of taking the packet, forwarding it, and spraying it to some other place. So the load balancing is one obvious use case for taking BPF, applying to Kubernetes. Another good area is around dropping the packets or filtering the packets, right? You have some PCI sensitive pods and services, and you don't want them going out to the internet. Yeah, you can just look at the destination header and drop them. So very efficient firewalling can be built, very efficient load balancing can be built using BPF, and that's the idea behind Cilium project, to take this powerful technique and help you run microservices at a large scale with higher churn much more efficiently, right? And Cilium is open source. It's a project, it was founded about slightly over 2 years ago. And this is a good artistic rendition of our ambitions. We want to tear apart the shackles of monolithic structure that are there in the Linux kernel, IP tables being sort of one of the representatives. So if you think of your microservices as a rocket ship moving fast or like a fast moving ship, these are kind of the anchors pulling you down. You should have seen the artwork, sketch work that we sent it to the designer, and the guy really amazing job with it, explaining and capturing the intention. So let's cover a little bit about what is needed from a least privilege network security perspective. That's a mouthful of a title. It's essentially just saying what pods can talk to which other pods and services internally, externally, within your data center, across the data center, and things like that. Just to illustrate the point, let's say there's a bunch of front-end NGINX kind of pod. There are some memcache services which are expediting the key lookup. You can have the front-end pod insert things into this memcache, but giving this front-end access to something like get all is probably disastrous. At this point, we all know that it's like a very expensive operation for memcache and causes widespread disruptions. Yeah. But that firewalling of what to allow and what not to allow is not an L3, L4 security, right? It's more of an API-aware security. Yes, front end can talk to memcache, but what exactly should it be able to do? It's becoming more and more important because we are taking this monolithic applications, which used to nicely talk using function calls, and we are replacing them with API calls. So previous security of nice function calls inside the operating system has gone into API communications over the network. So just doing an L3, L4 is insufficient. You have to go into enforcing API-aware security, and you can see the movement around this in Istio and MTLS and various other efforts making things API-aware. So that's the part which is inside the cluster. That's the sort of the east-west security. It has to go from L3, L4 to API-aware level. When things are going out, the identity outside the cluster is a little bit difficult to establish, but at least DNS-aware security is something that we should all aspire to achieve, right? Because DNS is a good identity for pretty much all external services. So we'll talk about how we can enable DNS-aware security. Last but not least is the part around who are we securing? What is the identity of this pod? In the good old VM days, you had a bunch of domain controllers, and you knew they were domain controllers, and they had a nice IP, and you could say, well, those are domain controllers. That's the identity of them, right? But now these pods are like shapeshifters, and they are running with one IP in one host, another IP in another host. They are alive for 15 seconds and dead after that, or something like that. So it's very hard to establish identities for these ephemeral, scale-out, high-churn environments. At least one approach is to take the metadata into account, what labels are there, or if you have crypto certificates into account to establish the identity. At least the three problem domains around the least privileged security is what I've tried to capture. There's the identity problem, there's the enforcement problem, and then there is the API-aware security problem, right? The enforcement suffers with one other problem of churn. These pods, as they come and go, their IPs as they come and go, that's where the monolithic structures like IP table start hurting. And that's where the efficiencies of things like BPF start coming in. I promise you I will end the slides very soon. The Cilium in a nutshell is essentially a software on top of BPF. It listens for the Kubernetes network policies, takes those network policies and translates it into BPF programs for ingress and egress rules, right? So it runs as a daemon set on all your worker nodes. It's listening for network policy objects. When the policies come in, it listens for them, it takes the policy input, and just attaches BPF programs corresponding to that. So that's the pretty easy way of understanding what Cilium does. This is why it can deliver all the power of BPF for your Kubernetes cluster. Yeah. It follows the same standard Kubernetes network policy approach. Default deny. The moment you enable a policy in a namespace, a whole bunch of things will go into sort of default deny. So applications will stop functioning. We will see some of that. So that's one of the more harder parts, how to iterate on the firewalls and securities and things like that. And it has same constructs like endpoint selector, ingress, egress, whitelist rules are all an OR of each other. Okay, so let's go struggle with the terminal, and hopefully the projections will be fine. But this is what I wanted to go over, rather than putting YAMLs and trying to explain what each of them are doing here. Let's just run them in the terminal in a smaller environment and see what's the impact. And we will try some of these policies, right? As I said, if you have policy disabled, that's a pretty bad security posture. Any pod can do anything within the cluster or outside the cluster. A sort of a good starting point, you could start with something like default deny, then nothing is happening, right? That's one posture. But a decent one that we have learned across many users is they just allow within the namespace to begin with. So all the services within the namespace are able to talk with each other. But you have to allow egress to kubedns. We'll see how you can do that securely as well. Then the other sensitive spot is around the Kubernetes API server. Since the API server, the backend points may or may not have any labels, it becomes hard how to establish the CIDRs for those API servers and things like that. So there is a construct in Cilium that can help with that too. But Kubernetes API server, as we learned from the recent the exploit and CVE alert, that it's a pretty sensitive, it holds the keys to the entire kingdom essentially. So we need to secure the Kubernetes API server for sure. And then we will look into more granular security. This is where the API-aware security comes in. We'll see how you can restrict the behavior of certain services when they are accessing other services at an API layer. Yeah. And then from an ingress perspective, there is an interesting challenge of whenever the traffic comes into a pod, into a service that is exposed at node port, you only see it coming from the host. So there is an interesting challenge around how to distinguish whether it's coming it's the traffic originally from host, or it is coming from outside and bounced via the node port, right? And this is important because there's a lot of health check kind of traffic from the kubelet, which is running from host to your pod. Those should be allowed, but not necessarily every pod should get a traffic from the node port, right? And so I'll explain some of the part of how we handle that. And then last, this is actually a pretty recent feature that we added in Cilium. It's around controlling the DNS lookups as well as the egress access based on DNS, so wildcard patterns and things like that. Okay. So before we jump into the terminal, though, just one double click on allow within namespace. It is a pretty decent, I think, what we have learned in practice from other customers is it's a good starting point. It protects a lot of these sensitive access points, API server, kubelet server, metadata services if you're running on cloud, any cross-tenant breaches if you have mapped your tenants to namespaces, and unwanted ingress, egress. So it's a decent starting point, right? So about my demo, right around 10:45 a.m. this morning, everything was working fine, then Minikube blew up. My backup plan was COPS cluster, but then the Wi-Fi here, just any kubectl commands were just not going through. So if you see a little bit of a paranoia in my face, it's because of that torturous experience for the past 1.5 hours. I downgraded to Minikube to version 0.28 or something, and then it worked fine. But 0.30 seems to be hanging in my computer at least. So in this Minikube cluster, I have a monitoring namespace. Many of you guys would have the same monitoring namespace, except probably for the Empire Dog. We are big fans of Star Wars. They were our early customer and inspiration. So that Empire Dog is essentially a policy dog fooding pod. We will see whether it can access things and things like that as we apply the policies. There is other namespace aptly named Empire, and it has just one service called Death Star. I borrowed it from Thomas's talk. Didn't want to create any new service in an Empire. So let's see how we can restrict the flows between these services. This should represent at least a couple of namespaces in your clusters which you already have, right? Jump to the recap. Let me escape out of here. Is the font okay on this one, or is it? It's okay? All right, cool. So as I said, we have a bunch of pods and services running here. In the monitoring namespace, there is the Grafana, Prometheus, and these guys. And Cilium is actually running as a daemon set, as I had said. It's running in the kube system namespace, but you can choose any namespace where you want to deploy Cilium. And there's only one node here, so pretty small setup. And if we look at the sensitive spots that I was talking about, this Empire Dog pod, our dog fooding policy, dog fooding pod, actually, if we try to go ahead and access the kubectl, looks like there is no authentication on this, and it can go ahead and access all the pods that are running there. Now, I'm not a very good hacker, but you could craft some really nifty commands and execute and get access to running pods and copy files and things like that. There's just no purpose of random pod having kubelet access, right? I do have the API access blocked. So if you look at this command, which is actually just doing the curl to go get that one, I do have authorization there. But this authorization is actually also very weak. It's just based off of the service account. If I change the service account on that Empire Dog to cluster admin, I'm pretty much sure it's going to reveal a bunch of secrets out of there, okay? But the basic point is this was a random pod that I created as testing. It just has a bunch of access without any particular rhyme or reason, yeah? And it can not only do damage by accessing this sensitive services, it can also go across namespaces and try to find services to exploit that are exposed. So this is our favorite, inspired from Star Wars, that you can actually go blow up the entire Death Star. That's what actually happened in the movie. They had a sensitive exhaust port open for HTTP put access. Okay, so how do we rectify this situation? I mean, it seems like it's a pretty happy situation from the application perspective. You can see the Grafana is talking to Prometheus. Prometheus is pulling the Cilium matrix, in this case, the drop count and endpoint. And so Cilium does expose a whole bunch of Prometheus matrix. From an app perspective, it's a pretty happy situation. These things are node port services. They are happily accessible everywhere from the world. From the security, it's not so good, okay? So let's just start with the within namespace, as I had mentioned. A surprisingly very simple step can go a long way to protect the service. One thing to highlight here is, you see all the labels are empty, but every CNP is, every network policy is scoped to a namespace. So when you push this policy, which says all endpoint selectors are allowing to go to all egress and ingress destinations, it's not all the pods talking to everybody. Cilium will insert a namespace label because it's already scoped to a namespace. So all pods within the namespace can talk to each other. That's what this policy will result in. You don't have to put the namespace in each and every where you want to apply this, okay? So let's apply this and see how that goes. While that happens, one other nifty thing to launch over here would be to just see the repercussions of these policies, whether they are functioning, sort of a TCP dump, if you would, for getting insights into what is getting dropped and things like that. Yeah. So let me exec into the Cilium pod, and I will launch a tool called Cilium Monitor. And I will restrict it to just show us the drops. Okay. So it looks like already after we applied this within namespace policies, a whole bunch of things started becoming unhappy. You'll probably get calls from your app developers that, hey, I can't access my Grafana and things like that. The calls to port 990, even the calls to UDP are getting blocked. Okay. So that's the first thing that we need to allow. You saw that there was no egress allowed in that within namespace rule. But without kubedns access, nothing is going to work. So let's rectify that situation. And the kubedns, to allow kubedns, you can use the same identity and label-based system. You can use the label called kubedns, allow specific access to port 53. So this is a good example of a combination of L3 and L4. It can't go to any other system on in the kube system namespace, any other service there. So it's a good limited policy. It's very liberal in that it's allowing you to look up any service and anything that is running internally or externally. And towards the end, I will cover how we can restrict even the lookups to specific services using wildcards and things like that, and enforce the egress there. Okay, so let's see if this helps the cause. Let me stop this and grep for port 53, right? Grep for UDP. That should also grep 53. We saw a whole bunch of these going by. Maybe nobody is making any DNS calls anymore. That's interesting. Okay, so let's create this kubedns -n monitoring namespace. This should get us the help that we need in order to have DNS egress, DNS lookups between the services. And let's just quickly take a look at what happened to all those sensitive points that we had. Oh, it didn't create? Oh, shit, I didn't pay attention. Thank you. All right, thanks for that. So this particular vulnerability had nothing to do with the DNS, with the DNS looker. It is directly hitting the IP, right? But now this is getting blocked because there is no ingress and egress allowed in this namespace. So it's a good spot to start with. And we can test the APIs and the Death Star explosion as well. It's just not going to be allowed. I will just show you the cross namespace one so that we make sure that the DNS lookup is working, right? See, it's not resulting in a DNS lookup error. It's just hanging for the curl to timeout. So that's the example of a policy L3 denied. Okay. There's one other thing. Since this is so noisy, there is one other option in Cilium which will help reduce it. So we can actually look at what all endpoints it is managing. So here you can see that it is managing kubedns, it's managing Grafana, it's managing all of these things. And this is like our Empire Dog test pod. We can just restrict the calls to this particular endpoint and say, hey, just show me all the drops related to this. Not this command, the Cilium monitor command, right? So that way it will become less noisy. And if I showed you one of these calls here, it should give you, it's resolved to the right backend service. It's going to port 80, but it's getting policy denied, right? So this is like a very simple starting point. We said, okay, allow within namespace. We said, okay, just allow egress to kubedns. But our developers are not very happy because we have taken away all their access, right? These things are not going to load. We have not allowed the node port services ingress from the world. That's also pretty easy to fix. So let's look at the allow from world. So there's the Grafana service. Again, using the same label-based identifier app Grafana, you allow it the access from entities called world. Now, the notion of world is also a little bit challenging. For Cilium, all the endpoints outside of the cluster are essentially classified as world, or for if any reason it can't resolve an identity, it just falls back as a world as well. Okay? But there's one interesting, as I had mentioned earlier, there's a distinction when the traffic is coming from node port versus a traffic originating from the host. If I allow all from the world, yeah, all of those traffic will go through. But by default, all the traffic from host is allowed. So how do we distinguish, right? How do you differentiate what traffic is originating from the host? Like a health check, you can have readiness probes and things like that from kubelet going into the pod. So what we do is when a traffic is originating from any of the interfaces inside the Cilium's host, we put a small marker in it, which will tell us that, hey, it is a traffic originating from the host. Using that, we can distinguish whether it is coming from the host or it is actually bouncing from an external, from an outside node port kind of a service. That makes sense? Grafana actually has a HTTP readiness probe, and you can see that Grafana is not failing, even though we don't have any ingress allowed. So ingress from host is always allowed. So let's create that policy of allow world, and hopefully the Grafana service will start loading after that. And note that even though the Prometheus service is a node port service, I have not allowed access to it, so that one is still blocked. So even though you have specifications or a service definition, you can still enforce controls. So this prevents, like, accidentally if somebody puts Kafka as a node port instead of cluster IP, and all of a sudden Kafka is exposed to the world, which it has no business being accessible from outside, often doesn't have any RBAC or TLS or anything to it, right? So you can have this safeguards in place which will prevent accidental misconfiguration from exposing a whole bunch of services unnecessarily to your internet. All those fancy graphs went away. By now you know the reason, because there is no egress allowed for Prometheus to scrape anything, right? We started with a very conservative spot. We said, like, just within the namespace, but Prometheus needs access to go and scrape a whole bunch of other endpoints. And Prometheus also needs access to the Kubernetes API server to go scrape those endpoints. Otherwise, it won't know what HTTP IP address it should go to. So first, we need to give Prometheus the Kubernetes API access. So let's look at now API server is a little bit of a tricky situation, because you may or may not have labels for the backends for the API server. It may be deployed as a pod, it may be running as a process in the host. But what we have here for those kind of scenarios where the backend can't be resolved reliably, or you have a headless service kind of a scenario, you just have exposed a headless service inside Kubernetes. There is a construct which we have created. It's essentially two services construct, this part here. And you can specify the name of the service and the namespace, and Cilium will automatically start tracking what are the backends for this, right? So if I push this policy, it will allow Prometheus to have Kubernetes API access. That Empire dog guy still won't have any access to the API server, okay? So let's do that. So you don't have to worry about creating a CIDR block or figuring out my API server. When the API server changes or scales out, you don't have to worry about tracking all of those. You just use the API specification, and it's going to go ahead and pull the backend information from there, okay? And so once we have given that access, let's look at the how do we want to enable the matrix access. Now, Prometheus is a good example of a service which only needs a restricted access. It has no point getting an access of a put or a post or a delete. It just simply does an HTTP GET, and that's all it needs for a legitimate action, okay? So if let's say Prometheus pod gets compromised and you don't have any API level security, you have just given Prometheus access to all of your endpoints, potentially even port 80 endpoints that have /matrix exposed. And if it gets compromised, you have a whole bunch of post and deletes and random actions going on over there, right? Just piggybacking off of a really allowed transaction. So for that, what you can do is, using Cilium, you can specify the labels, you can specify the port, that hey, the traffic can go to any port 9090 and scrap the matrix, or any port 80, but you can restrict it to just doing an HTTP GET, nothing else. You can't do put, can't do post, delete, none of that. And this actually leverages Envoy. So in order to parse the traffic and filter, Cilium has an Envoy built in. It will route the traffic using socket redirections and such, and efficiently parse it out and block the traffic. Okay. So let's find the Cilium endpoint for Prometheus and put that over here so that we can monitor what is going on. So this is the endpoint list for this. So we say Cilium monitor -- this guy. You see it's having a lot of drops, right? It's going to various places and it's not able to reach anything. So let's first push the matrix.yaml. This will start functioning, and we can see the effect of that in the Grafana dashboard as well. So once I refresh this, hopefully the matrix should start coming in, and there you go, the matrix starts coming in. The Prometheus is just very chatty, so it's kind of hard to parse what is going on over here. That's why I created that Empire dog. Otherwise, it's kind of hard to know what is getting dropped. So now we have our application functioning back. This is much more secure than the previous, what we started about 10 minutes ago. Everything is allowed to talk to everything. Here, and monitoring is a very good application to relate to, but you have many different services which are probably don't have any policies in place. This way you can iterate one step at a time, and you can just allow the services that you want. The key question that arises, how do I know what to allow and what not to allow? And that's, at least you see the direction over there that Cilium exposes a socket, a set of logs, and communication that's going on. That information can be used to build who should be allowed, who is getting dropped, and things like that, right? One other policy that I wanted, as I mentioned earlier, was, so these are all the policies that we applied already. Now, the question of external egress access. So let's say our customer, the Star Wars Empire Foundation team, they want to back up the matrix, right? So they want to put an agent inside the Prometheus, and they want to take a copy and put it in S3 or something. Now this kind of a backup service is very common, but again, this backup service should only be able to go to S3. They should not be looking up at cryptomining.com or something like that, right? So let's see how we can restrict the. And this one, I'm going to make it a little bit bigger. So again, the test, our dog fooding app over here, and the same label-based identification for kubedns, same port 53 access, but we have added one more condition here, which says that you can only do DNS lookup for S3 and Amazon AWS, like star.s3. Any region inside Amazon AWS. You can't even look up anything else. You are a backup service, you have no business looking up anything else. This is really tightening the knot to the, like it's just truly least privilege for any of the pods and services, that you can't do anything more than what you are required to do. The second part of it is, okay, fine, you have done the DNS lookup, where can you make the TCP IP connections to? And that's this part which says like, well, those are the domains you can look up, and those are the domains that you can connect to. So same pattern-based FQDN rules which will control egress, and you can combine them with the 443. Now, one of the challenges with the external service access going over TLS is there is no good way to do TLS visibility unless you want to go try out trusted man in the middle models, and that's some of the things that we are working with around KTLS. Once that is there, you can even add sections. What exactly can you do? This service should just be able to put, and that's it. It should not be able to get all the buckets and things like that, because you may have other buckets there. So you can see the direction of where this is going. Right now, it controls access to external service on a port and a DNS level. Once we have the KTLS and those things sorted out in the kernel and enforcement, then you'll see the HTTP clause over here as well. Then it will again very tight security around this. So let's see if this pattern-based policy works. This is very new, so I pulled in the nightly build from a couple of days ago. So let's see if it cooperates. Right, so and I'm going to go use to access some of our public assets that we have. Now it should be allowed to go to this star.s3 US West 2 region, right? Because that matches the pattern. It's going to a particular bucket in a particular region, and I don't have any tokens enabled. So the L3 communication was allowed. It failed at an access denied L7 level. Okay, so the pattern-based enforcement and things like that work. And let's say if it can go to google.com or twilio.com or something like that. This should not even allow it to do a DNS lookup. We should get a resolved host error or something like that, right? Because we didn't even allow it to do DNS lookups. This prevents against IP spoofing and DNS poisoning and those kind of attacks. Since we are using so much of DNS now, it's only a matter of time that they rear their head. So just a quick recap. This is all the policies that we enforced. We started with allow within namespace. Then we talked about pattern-based DNS, API aware, and why that is needed. We used a special construct like toServices to secure the Kubernetes API access. We used a special construct reserved world to control ingress, egress, and then I described how we distinguish between the host and the world traffic. Okay. There's a lot more API services that are very common, so we have added support for them. More importantly, we have created a extension framework for Envoy. So there is a Golang-based extension framework. You can write your own custom protocol, or if you want to contribute to one of the popular protocols, that's also pretty easy. You can use Go-based Envoy extension to do that. Okay. I've added this here. If somebody is browsing the slides later on, this is the same policies that I showed over there. And this is some of the newer stuff that is coming in. Now, securing one of the clusters is one thing, but pretty much every customer that we talk to now has many clusters for one reason or the other. And there is often a need to share the access across multiple clusters, use the same service identity across different clusters. So what we have done is created a notion of cluster mesh. It's a very easy way to set up connectivity across multiple clusters. And the security identities also are across all the clusters. So if you have that star service running in one cluster and also in another cluster, it will get the same security identity. And this is available, I think it's already posted as a blog in our 1.4 preview. More of the details are available in Thomas's talk on how we actually do it by reading the etcd across each of the cluster and understanding the identities. But on your part, the effort is really around how do you secure the connectivity across these clusters at a lower sort of L2 fabric of do you need to create IPsec or VPN gateways and things like that. Once you have established that connectivity, we can take care of connecting all the Kubernetes services and securing them. And this is personally my super favorite. I'm very excited about the opportunity that KTLS will unlock. A lot of the sophisticated compromise that we see now are actually piggybacking off of an encrypted channel with authorized tokens and everything. And the fundamental problem there is just visibility. You don't even know who this compromise is, what they're doing, just they're going in the encrypted channel. So KTLS is a really nifty concept. The asymmetric part of the exchange happens just like it happens always, right? The client and the server, they will do the asymmetric key part. Once the handshake over there is done, the symmetric key is offloaded to the kernel. So then the kernel will do the encryption for you. You don't have to worry about doing that encryption in the app. So what is the benefit of this? Between the user space and the kernel, the packet is unencrypted, and that's where you can attach a BPF program and inspect the headers and things like that, or redirect it to a proxy. So you can get visibility and enforcement in a TLS communication before the symmetric encryption happens on the data payload, right? And the biggest benefit of this is no root CA propagation, none of that multi-chain certificate headaches of where all do I need to propagate the root CA, okay? So this is personally my favorite new feature. It's going to be a little bit of a grind to get it out, but it's definitely very powerful. But in a nutshell, you see that this is why I started with BPF. Like the programs, it allows you flexibility to attach these programs at various levels, whether for TLS visibility, packet filtering, firewalling, and things like that. And Cilium is just making it easy for you to tap into this power and run it in the Kubernetes in your cluster. I survived that talk, so that's pretty good.